This class exercise will let you practice various methods for estimating total impervious area, TIA. Please see the SELDM video on TIA for more explanations. This is training module 2.06b for the Stochastic Empirical Loading and Dilution Model SELDM. This presentation has 17 slides and will take about 6 minutes. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This module has 2 learning objectives. We will explore 5 methods for estimating impervious area, including road density, percent developed area, census data, land cover, and Streamstats. And we will learn that different estimates may yield similar lag times and runoff coefficients in relatively undeveloped basins. Today we will use Howard Brook Basin in Northborough, Massachusetts above Highway I-290. The basin is the pink area outlined in black. The highway is highlighted in light blue in the lower right corner of the image. The latitude and longitude of the basin are about 42.335 and minus 71.665 respectively. Above this point, Howard Brook has a drainage area of about 1.34 square miles, a drainage length of 12,619 feet, a main channel slope of 150 feet per mile, and a basin development factor of 0 because it is a natural, unmodified channel. To use percent developed area to estimate total impervious area, TIA, draw polygons around the developed areas, sum those areas, and divide by the total basin area. I get a value of 5.79 for the percent developed area. The developed area equation, which we discussed in the module on imperviousness, yields a TIA value of 0.014 or 1.4% for a developed area estimate of 5.79%. As this screen capture image indicates, the Streamstats estimate for PDA, defined here as percent urban, is 7.8%. The developed area equation yields a TIA value of 0.0198 or 1.98% for a developed area estimate of 7.8%. To use road density to estimate TIA, measure the roads, multiply by the map scale ratio, and then use the TIA regression equation. I used the Adobe PDF measurement tool and got a length of 3.52 miles and a density of 2.63 miles per mile squared of roads. The road density equation, which we discussed in the module on imperviousness, yields a TIA value of 0.0097 or 0.97% for a road density of 2.63 miles per mile squared. The Census Tiger data indicates a population density of 542.2 people per square mile in the census block 7401.01. In this case, the census approach is easy because there's only one block within the stream basin. The population density equation, which we discussed in the module on imperviousness, yields a TIA value of 0.057 or 5.7% for a density of 542.2 people per square mile. This is higher than the previous estimates. Howard Brook is less densely populated than other basins within the census block, and, as we could see on the graph, TIA varies widely around the regression line. If you want to use index TIA values with the National Land Cover Dataset land cover categories, then you may have to learn GIS. Things start to get complex even on a small watershed. There are many small areas and areas within areas. You need to get the various areas, then multiply them by the land use based impervious coefficients. However, TIA estimates for various land cover classes vary widely, so a seemingly precise answer may actually have more uncertainty than simpler methods. In many states, Streamstats now provides TIA values for one or more time periods. This estimate for Howard Brook is 0.0181 or 1.81%. Now, we can use the regression equations to predict the average, standard deviation, and skew of runoff coefficients and the basin lag time from TIA to compare the effects of the different TIA estimates on these hydrologic variables. The results in increasing TIA order indicate that differences in hydrologic variables are small. With TIA estimates ranging from 0.97 to 5.7, the average runoff coefficient varies from 0.131 to 0.142. The standard deviation of runoff coefficients ranges from about 0.99 to 0.1. the skew ranges from 1.075 to 1.048, and the basin lag time ranges from 1.248 to 1.225 hours. Differences for highly impervious basins would be much greater. For example, if the TIA ranges from 90 to 95%, the RV average would change from 0.655 to 0.712, and the lag time would change from 0.52 to 0.41 hours. Most basins, however, have low TIA values. For example, in Rhode Island, the second most densely populated state, 19% of the 3,024 basins above roads have TIA values less than 1%. 56% of basins have TIA values less than 10%, and about 90% of these basins have TIA values less than 40%. The TIA regression equations are available in Appendix 6 of Technical Report FHWA-HEP-09-005. In this training module, we learn about 5 methods for estimating total impervious area. We used the percent developed area, road density, census data, land cover, Streamstats. We also learned that different TIA estimates may yield similar lag times and runoff coefficients in relatively undeveloped basins.